We present the k-type normal distribution, which is a compact parameterization of Gaussian mean-field posteriors in Bayesian neural networks. In Bayesian neural networks, we are interested in learning the posterior distribution over the network weights. A popular approach for doing this is variational inference. In variational inference, we approximate the true posterior distribution using a simpler distribution Q. A common choice for Q is a multivariate Gaussian. A key object here is the covariance matrix, which can become very large. Therefore, the standard approach is to make a mean-field assumption, which results in diagonal covariance. However, many consider this to be a too restrictive assumption and explore richer parameterizations. We question whether this is needed and study the opposite direction of even more compact parameterizations than mean-field. In our method, we consider the elements of the diagonal that belong to a specific layer. We then reshape these elements into the shape of this layer. Finally, we studied the low-rank structure in such reshaped matrices of that diagonal elements. In our experiments, we take a two-step approach. First, we train the standard mean-field Bayesian neural networks and investigate their low-rank structure post-training. Second, we check whether we can directly train the low-rank parameterizations, where the vectors u and v are the new parameters to optimize. As just mentioned, in the first step, we train the standard mean-field Bayesian neural networks and investigate their low-rank structure post-training. In particular, as seen on the previous slide, we investigate low-rank structure in the reshaped matrices of posterior means and posterior standard deviations. In our experiments, we observe that the matrices of standard deviations display a strong low-rank structure, while this is not the case for the posterior means. Importantly, we observe the same phenomena for different model architectures, different model sizes, and different layer types. This suggests the generality of our low-rank structure finding. In the second step, we investigate whether we can directly train our proposed low-rank parameterizations. We find that the low-rank parameterizations significantly increase the number of training parameters while matching the test accuracy of the full mean-field parameterization. More importantly, we observed that the low-rank parameterizations significantly decrease the signal-to-noise ratio of the gradient estimates of the posterior standard deviation parameters. This also translates into increased convergence speed of the negative elbow training objective. These results are important because the high variance of the gradient estimates is one of the biggest challenges in Bayesian neural networks. To sum up, our contributions are the low-rank structure observation in the mean-field posteriors, and the k-type normal distribution, which increases the signal-to-noise ratio of the gradient estimates and as well as convergence speed, while decreasing the number of model parameters. Thank you.